Well, we're starting on a brand new topic. Can you guess what it's called? Yeah, electric charge. You're so clever. Now, electric charges are something you would have heard about before, but we maybe have a little different way of approaching things in this class and for the AP test. Think back to when we talked about universal gravitation. The idea that when we put a mass, some object that has mass, in some location, it actually changes the space around it. Not just that it affects the objects around it, but it changes the empty space around it, some characteristic of that. We said it sets up a gravitational field around it. Well, electric charges, or things that have an electric charge, do the same thing. They change the space around them. So in this unit, we're going to be looking at how space can be changed by an electric charge, how that affects other electric charges in the area, and just some applications for those processes as well, including some basic electric circuits. We'll keep coming back to this idea of gravity and how it's similar to electric forces, electric interactions, though we will find there are also quite a few differences between the two. So with gravity, we place some mass in space, and that causes a change in the space around it. And we can put a little mass or a big mass there. That will determine how much the space is changed, but the quality of the change, the quality of that field, that it pulls things toward that mass, that doesn't stay the same. So when we look at a pair of objects with mass 1 and mass 2, we have this interaction between the two, but it's always going to be an attractive interaction. We've always got to have gravity toward each other. We don't ever have repulsive gravity. And that's where we find our first difference between gravitation and electric forces. We only have one type of mass. We don't have like a positive mass and a negative mass, or a north mass and a south mass, but we do have two different types of electric charges. We distinguish those as positive charges, drawn here in red, or negative charges, drawn here in blue. And the sign on that charge, the type of charge that we're dealing with, determines whether we get an attractive force, which happens when we have opposite charges, or a repulsive force, which happens when we have like charges. So two negatives will repulse each other, two positives will repulse each other, a negative and a positive will attract each other. Now, something that electric forces have in common with gravitational forces is how the magnitude of that force is determined. Both with gravitation and with electric forces, the strength of the force depends on the product of whatever that property is that's causing that force to exist. So for gravitation, it's mass. For electric forces, that's charge. So it's the product of the two charges here divided by the square of the radius between them. We write this in an equation called Coulomb's law, which is expressed on your equation sheets like this. The magnitude of the electric force is equal to Ke, which is called the Coulomb's law constant, times Q1, Q2, and that's an absolute value here, divided by r squared. So this equation gets us the magnitude of the forces, but we do have to pay attention to whether they're positive or negative charges, whether they're same charges or opposite charges, to figure out whether this is going to be an attractive or a repulsive situation. Now Ke, the Coulomb's law constant, that has just some value to it. It's a coefficient that'll basically convert this this number into newtons for us. So the units on this are 9.0, or sorry, the number for this is 9.0 times 10 to the 9th, and then the units are Newton meters squared per Coulomb squared. Now at this point we define charge, and you may think, well, that seems a little backward to talk about how charges affect each other and then later on to define charge, but really when you understand how we look at charge and how we understand it, you see that we only know about charge and this property of materials based on how they interact with other charged objects. So it's only through examining these things with Coulomb's law and related equations that we have any way of detecting what the charge is on these objects. So charge it's a property of matter, which isn't necessarily a very satisfying description for anything. It's just a characteristic. Where does charge come from? Well, at some level, we don't really know. We can define what the charge for some larger object is. We know that that comes from the fact that it's made up of protons and neutrons, which themselves are charged. So if we have an imbalance of protons and neutrons, we get a net charge on the object. The protons and, I think I said neutrons a second ago, but I meant electrons. The protons and electrons are very small particles. The protons can actually be separated into quarks, which have fractional charges, but beyond that, we don't really have a good answer. We know that these particles have charge as one of their properties, but as far as what it is, what it looks like, what its substance is, we don't really have a good answer for that. Just that it is. We know that there are two varieties of charge, and again, why are there two varieties? Why not three? Why not just one? Well, we don't have a great answer for that. It is, though, we know that much. There are two varieties, and we call them positive and negative. Positive and negative are sort of an arbitrary way to name these. It works nicely with some of the math we do. With magnets, we use north and south for the two ends. And so it's kind of the same idea as that, but just a different notation, a different way to separate the two different types of charges. To quantify how much charge something has, we measure it with a unit that we call coulombs, and since we have two different flavors or two different varieties of charge, we could have a positive number of coulombs or a negative number of coulombs. You might say, well, what's a coulomb? How is that defined? What's that related to something that I know? Well, we can compare this to the charge on an electron. An electron, of course, is a little tiny piece of matter. It has a charge of, well, for an electron it would be negative 1.60 times 10 to the negative 19th coulombs. Protons have the same value for their charge, but a positive charge instead of a negative. And so all objects that we build out of protons and neutrons and electrons, neutrons, by the way, have no charge, no net charge. If we build them out of protons and electrons, which have charges of plus E and minus E, respectively, the total charge, the unbalanced part of our charge for any larger object, has to be some whole number multiple of E. So if we have 5 protons and 3 electrons, we've got plus 5E and a negative 3E. So we have an overall non-balanced charge here of plus 2E. Now we can't have any number that isn't a whole number multiple of 1.660 times 10 to the negative 19th coulombs. We call that the fundamental charge. That's like the building block. That's the smallest increment of charge that we can have. Because it can't be any value, it has these discrete values that it has to be. We say that charge is a quantized quantity. Quantized just means that it comes in packets, discrete amounts of charge. It's not continuous, which would mean that it could be any value. Now you might find yourself wondering with these charge interactions, Why should we care? It doesn't seem like they play a very big role for us. Maybe we feel a little electric force when we scuff our slippers on the carpet for a while and then touch a light switch, but other than that, do we really experience electric forces very often? Well, yeah, actually we do. When we look at the structure of an atom, we see that the parts in the middle, the nucleus, we've got positive and neutral components there. So positive protons, neutral neutrons. The electrons, which are whizzing around sort of in orbit around the nucleus, those are all negatively charged, and they don't stick with the nucleus unless we have these interactions, these charge interactions. Over that distance, the distance from the nucleus to where the electrons are, the electric force is really a remarkably large force, large enough to keep these electrons, which move at incredible speeds, close, tightly packed around the nucleus. Well, okay, not tightly packed, but they keep it from moving somewhere else, or at least usually they do. Sometimes they escape, sometimes we capture new ones in this nucleus. But without that charge interaction, we don't have the electrons staying near the nuclei for atoms, which means we don't have atoms or atomic structure and molecules and all the stuff that is made out of molecules, which is everything, that we know. So the charge interactions, they're absolutely fundamental. Aside from applications like electricity, being able to turn on a light switch, that's obviously got some electric interactions with it, but the very fact that the light switch exists, that it's not just a pile of protons and neutrons and electrons drifting off in space somewhere, that's solely because of this charge interaction, this electric force. I mentioned that the electric force is a very strong force, and you might be skeptical about that. You might think, well, okay, strong, but not nearly as strong as something like gravity. I mean, gravity makes us go around the sun, and it keeps me from flying off the earth. And when I run and trip, it makes me skin my knee, and I experience this gravitational force all the time, and so I can't possibly be nearly that strong because I don't even notice the electric force, but I notice the gravitational force for sure. Well, no, actually, that's not the case. The electric force is quite a bit stronger than the gravitational force. Much stronger? Well, if we imagine that we put two protons somewhere next to each other, those two protons have the same charge, so they're going to get repelled by this electric force. So they each get a force away from the other one, this electric force. But they each also have mass, and we only have one type of mass here. Masses always attract each other. So they've each got a gravitational force as well. Alright, so those are probably roughly in balance then, right? Well, no. Not, just no. No. How out of balance are they? Well, the electric force, the magnitude of that is roughly equal to the gravitational force times 10 to the about 42nd power. The electric force is 10 billion million times stronger than the gravitational force between these two protons. So the question remains then, why do we experience the gravitational force so much more frequently, or why is it so much easier to notice than the electric force? How come we can tell that we're falling down because of gravity, but not that we're flying around the room because of these electric forces? The answer, in short, is that gravitational forces are all attractive. There's no repulsive component to them. if we model two objects as just kind of these blobs of mixtures of positive and negative charges, for every positive charge that we have over on this side, we're getting a repelling force from all the positive charges over on this side. So this little positive charge gets 1, 2, 3, 4 repelling forces from these 4 charges over here. And it gets attractive forces from every negative charge over here. So it gets 1, 2, 3, 4 attractive charges. Now this negative charge here gets 4 repulsive charges from each of the negatives over on this side, and 4 attractive forces from each of the positives over here. And so we start to see how there's this balance between those. That those forces can be attractive or repulsive, but on average, since we typically have positives and negatives in roughly equal amounts, those forces balance each other out for bigger objects like you and me and a tennis ball, and really anything above the atomic and molecular scale under normal circumstances. We've gotten lots and lots of charges, but they're basically even in their amounts. And so it's only when we have unbalanced charges that we get this interaction, this noticeable interaction, a net force in one direction or the other. If we looked at the charges over on the left side here, the positive charges get repulsive forces from all the positive charges from the thing on the right side. So this one gets a repulsive force from each of those positive charges, and it gets an attractive force for the negative charge. It's over on the right side there. The negative charge here gets a single repulsive force and 2 two attractive forces, one for each of those positive charges. And then these 2 positive charges, they get 2 repulsive forces, one for each positive charge on the right side, and then 1 attractive force. And we can see that while these do largely cancel out, we've got 1, 2, 3, 4, 5 repulsive forces and only 1, 2, 3, 4 attractive forces. So we do get this net force pushing this object over to the left. And if we repeated this for the object on the right, we see the same kind of thing. So each of these positive charges gets 2 forces away from the other object and 1 force toward for the one negative. The negative gets 2 forces toward for each of the positives, 1 force away for the negative, and then this gets 2 forces away and 1 force toward. And so we see the exact same thing just mirrored. This has a net force of 1 arrow, whatever that represents here, to the left. This one has a net force of 1 arrow to the right, which should bring to mind Newton's third law here. The force, the overall force that this object experiences is the same magnitude, 1 arrow worth of force, but in the opposite direction as the one that this one gets. This one gets a force to the right, this one gets a force to the left. And so when we're looking at the forces between charged objects, you might be given a value for the charge of some, say, a metal sphere. We're not really looking at the every single charge that is on that thing. We're just looking at how many charges are unbalanced. It's the unbalanced charges, so that is the extra positives or the extra negatives, beyond that 1-to-1 ratio of positive to negative. It's those that are responsible for the net force. So if I said that an object had a charge of plus 5 coulombs, which would be a huge charge, by the way, what I mean is that there are lots and lots of charges within this thing, lots and lots of positives and lots of negatives, but the positives outweigh the negatives. There's more positives than there are negatives. How many more? Well, in this case, 5 coulombs worth of extra positive charges. That's not the total number of charges, just how many extras of one type or the other do we have. So now if we're trying to calculate the force between 2 charged objects, and again when we say charged, we mean that it has extra positives or extra negatives. All objects have charges in them, but most of them we have a balance between positive and negative. So here we have two charged objects. We want to find the force between these two. Let's say the force that acts on this positive charge over here, both the magnitude and the direction for that. Well, direction we can do straight away here. We see that one of these is positive and one's negative. Those are opposite charges, so these are going to attract each other. So electric force is going to point toward the other object. They each get the same size force, just in the opposite direction. Now, how big is that force? We can determine the magnitude using that Coulomb's law equation. So the magnitude of the electric force is going to be K, which is 9.0 times 10 to the 9th Newton meters squared per Coulomb squared. Write the units out in your constants. It helps you to remember to check for your correct units. I see meters, and remember, yeah, my distance has to be in meters. And coulombs, and remember, yeah, charge has to be in coulombs. Ooh, and it's not. I've got these prefixes out in front here. This would be an excellent time to review those metric prefixes if you haven't done that for a while. I forgot to put in here, these are absolute values, since it's just for the magnitude. So I have the absolute value of, let's see, that's 3.0 nanocoulombs is what the lowercase n and the c means. Nanocoulombs is 10 to the negative 9th coulombs. And then negative 5.0, that's Greek letter mu, so that's microcoulombs, which is 10 to the negative 6 coulombs. Now, why so small? Because a coulomb is a really big unit of charge. So we'll see these prefixes pretty frequently here. Divided by the distance between them squared, and that needs to be in meters. That one already is. And so we get an electric force then of 0.0135 newtons.